groups that we have with us. Now if we go down a little bit, so let's say that I want to just look at the petal dimension now. I don't want to look at the sepal, I just want to look at a particular dimension now. And that's basically this cluster of points. That's what we have. So I plotted the petal length versus petal width, and I plotted all those points. Now we can clearly see this is one cluster, and they're like quite close to each other. So the variance is smaller in this case. Whereas this cluster is quite stretched out. So there's a lot of variance. And probably there are 3 classes because you already know in advance. Like if I showed you this data set, it's very hard for somebody to say they are 3 classes or 2 classes or 4 classes. We don't know that. But here we already know it's 3 classes, but we kind of see that one class is quite separate, but the other 2 classes are kind of mixing in a way. There is no distinct boundary that separates these 3 classes. That's what we have here. So now I just run this k-means thing. So this is my data matrix, and I say just break them into 3 clusters, and what I end up is basically IDX is basically the label, the cluster label assigned to each data point, and C is basically the centroid. Because I know, because that is basically the class president of each cluster. That is telling me that all the variables from that center are close to each other. That's what we have here. So the next thing I just do it, that I just compute a distance map, and I just try to sort each point on the grid. So I have a 2D grid, I have these centroids that are coming from this C. Now I'm saying that every point, because if you look at this thing, let's look at this thing. This is very interesting. Who says that you can't have a species, a new sample, which has this data point here? It is possible. I don't have the data point here, but that could be a novel data point. Who says a novel data point cannot be here, cannot be here, cannot be here? So in other ways, what I'm trying to do right now is I'm trying to classify every 2D point, every point on this 2D grid. I know the centroids. I want to classify every point on this 2D grid belongs to which cluster, which does not sound to be like a senseless problem. Because every point on this 2D grid can be a possible petal dimension of a new sample that our model has never seen. So that's what I do. So I just create a distance map, and I just compute, again, I cluster k-means grid, and I know that these are my starting centroids, which I've already computed. And all I do is that I assign these regions. And that's, for example, what we have here. And we can clearly see that these are hyperplanes, 1 and 2 hyperplanes, which segregate the space into 3 clusters. And we have cluster 1, cluster 2, cluster 3. This is just one iteration, by the way. And we can see, for example, here that it says, if I go down, that it failed to converge in 1 iteration. So let's say that if I change the number of iterations, let's say 20. Now it has converged, and you can see now. At first, the hyperplanes were inclined, they had negative slopes, but now they're all vertical hyperplanes, because now it has converged. And this is a possible segregation, not exactly vertical, but yeah, it's more vertical than the previous ones. So these are a possible class of unsupervised learning based on this data, and I can classify any point. So give me any point. What I do, I just put that point on this map, jo usko color assign hai, that is basically the classification. So just using unsupervised learning, I can classify my object. Because I don't know the actual annotations, but I constructed my own clusters based on the hidden features, hidden properties, hidden essence in the data. And now whenever a new data comes, I can predict something. So anything that falls in this sector is class 1, in this sector is class 2, in this sector is class 3. That's unsupervised learning without any manual annotations. Ji Janab. I don't think so. No, okay, the one basic essence of k-means clustering is all the clusters are disjoint. All the clusters. Yes, if you do something, let's say, I won't use the word clustering, but let's say you want to have some probabilistic estimate, then it could be, okay, one cluster is saying, okay, for one point it is a 60% chance in this region 2, but here they are disjoint clusters. We have to make some decisions. We don't know. So we can't say. Unless we have some extra information that we can incorporate. But here, whatever it best did, it said whatever is less than or equal to this thing, it falls there. If it is greater, it goes there. It's a hyperplane. Yeah.
So what if something from cluster 2 falls into the very edge of cluster 1?
It could be properly classified, it could be misclassified. There's an issue, there are all sorts of questions that are out there. So we could have that. We could have, so nothing is perfect, guys. Nothing is perfect. There is no ideal situation. There is scaling.
Is it the data itself that the boundaries are so straight?
Probably. It could be, if it was a data which was, I think there's this data, I forgot the name, which have these points on the circular thing. So you have, so what you do is if you have, your surfaces are circular surfaces. But just the nature of the data. Yeah, it's just the nature of the data. It's a very, very simplified problem. That's fine. All right. Okay. So now I won't go into the, I won't go into the detail of reinforcement learning. I'll just mention very, very briefly because I think there's some more important things that I want to cover. So in this case, what we are saying that instead of having a completely annotated data set, we have some outputs and we have some beliefs, some grades that have been assigned to that output. And based on these beliefs or grades, I can actually come up with some reward or punishment. And I can say, okay, take this action, it will help me classify something better, it will help me regress something better in future, or don't take this action, it is going to lead to more misclassification or more regression, or more misregression. That's what we are trying to do. So you have the same learning scheme, but now we have some correct outcome with some beliefs. It's not exactly, it's not the most proper, like in supervised learning, there is some belief attached to it, and based on that belief, I can always come up with a reward and a punishment mechanism. And I tell my agent that if it is a reward, take this step because it is going to benefit you in the long run. Because again, we don't want to chase the performance there. At some point, there is a policy that I can compromise on a reward now so that in the long run, I'm getting some reward. So I'm trying to reinforce the decisions that I'm making based on some output and its beliefs that comes with the data. That's reinforcement learning. So it's not as simple as supervised learning or unsupervised learning, and there are like, okay, we don't require any complete input-output pairs. That's a good thing. But it's very difficult to get manually annotated, perfectly annotated data in every discipline. So there is no supervisor. It's just reward and punishments based on those beliefs. Your current actions will always influence what you do with incoming data. So you have to be very careful that what actions are you taking. You are always looking for a long-term reward rather than for intermediate rewards.